Thank you very much. I would like to thank the organizers very much for putting on the conference and for the invitation to speak here. Particularly Colin, I'm very sorry that he couldn't be here, and I hope he's feeling better very soon. So I promised to give something of a survey talk where I try to explain, mainly I'll try to focus on some recent conjectures about the distribution of resonances for hyperbolic surfaces, and also some theorems related to those conjectures. So I wanted to start by laying out some of the contexts in which this theory applies. And some of this is more general than I'm going to be later, but in general, I'm always going to consider a non-compact, complete Riemannian manifold. And the model case is really an exact hyperbolic quotient. So always geometrically finite. If it's not geometrically finite, there's very little we can do for the spectral theory. So we always assume geometrically finite, which in particular means topologically finite. For surfaces, the Euler characteristic will need to be finite. Some of the statements I'm going to discuss apply in finite volume, but generally I'll be concentrating on the infinite volume case. And some of the statements I'm going to make apply in the presence of cusps, and others don't. So those are possible variations. And then sort of one level generalized from that, you could consider a manifold with hyperbolic ends, which for the purpose of this talk, you could think of as just a compact metric perturbation of a hyperbolic quotient. So essentially you allow the metric to be arbitrary inside some compact set, and then make it look exactly hyperbolic at the ends, and also in the sense of being geometrically finite. And then another level of generalization up would be to consider asymptotically hyperbolic manifolds, which have come up in some of the other talks this week. So those would be, in general, when you say asymptotically hyperbolic, you mean conformally compact, which means that you don't allow cusps. And in general, when we look at these different categories, we're trying to sort of understand which spectral properties depend on what kind of information. So in the first category, you tend to have techniques based on algebra and analyticity. And in the second category, it's sort of basing arguments on geometric models. And then the third category is essentially doing spectral theory based on the microlocal structure of the operators themselves. So if you can sort of move results from one category to another, you can figure out that certain results do not depend on the geometric structure, but depend only on the microlocal structure of the operators, for example. So we're very interested in trying to figure out which results can be moved from sort of less general down to more general, just to kind of understand the structure. So I'm always going to be considering the spectrum of the positive Laplacian operator, which is typical for spectral theorists. And my convention will be the dimension is n+1. And just to list the basic facts about the spectrum, which have already been mentioned in various talks this week, in all of these categories, there's discrete spectrum below n²/4, and absolutely continuous spectrum above n²/4. And in the cases I'm mostly talking about, the volume is infinite, and there are no embedded eigenvalues in such cases. And in all of these examples, if you write the write the resolvent with the spectral parameter in that form, you get a meromorphic continuation to the complex plane. So this is essentially a double cover of the usual spectral parameter that allows you to pass through the continuous spectrum. And to define that meromorphic continuation, you need to restrict the resolvent, say, to compactly supported smooth functions or to some weighted L2 space, for example. So this whole spectral picture in the hyperbolic case was worked out by Lax-Phillips in the first place, and then generalized to the asymptotically hyperbolic situation by Matteo and Melrose. And then actually the final piece of this puzzle was the most difficult sort of analytic continuation argument is in the case where you have higher dimensional hyperbolic manifolds with cusps that are of non-maximal rank. That turned out to be rather a thorny issue that was finally resolved by Guillaume and Matteo in 2012. So the resonances, this has already been discussed in various talks, are poles of this meromorphic continuation of the resolvent, with multiplicities counted by the dimension of the residue. There are two different ways that this is commonly written. So the These have actually both appeared, I think, in previous talks, but just to sort of make it clear that we're all talking about the same thing, if I write the spectral parameter in the first way, then the critical line ends up n over 2, and sort of the resolvent set is over here, and the resonances appear when you analytically continue across the critical line, so they appear over here. So this is really kind of the Selberg viewpoint. That's the motivation for that parameter in the first place. And then the second view is actually the traditional scattering viewpoint, where the resonance set is up here and the poles appear below the axis. And there's always the conjugation symmetry. In this case, it's literally complex conjugation. In this case, it's a reflection this way because of the self-adjointness of the operator. So this is basically traditional. And they're both completely natural ways to draw this picture, and so we just have to live with the fact that we sometimes switch back and forth between them. So let me just show you a picture. I'm going to attempt a hybrid talk here where I switch back and forth between my slides and Mathematica to show you some pictures of resonances. So let me just show you what these look like in certain cases. So for example, here's a plot of the resonances of a surface that was described in Mark Pollicott's talk on Monday. Is that visible? I can change the resolution if it's not apparent enough. So this is actually the plot of resonances for a symmetric pair of pants. So if you take a hyperbolic pair of pants, then its moduli space is parameterized by the lengths of these geodesics. And so you have three real parameters describing the surface, and this is the plot of about 100,000 resonances for the case when all of the lengths are equal to 7. And so the first resonance, which has been discussed in various talks, appears right there. And I'll have more to say about the distribution in just a second. But these resonances fall on kind of exotic curves that line up in various ways. Let me just show you another one. If I move slightly off the symmetric situation, I believe it was 8,000. Yeah, that's up to 8,000. The length, 7 in this case. So these, I should perhaps mention a few things about this picture. First of all, this the technology used to compute these was developed in a paper with Tobias Weik. And, but the actual technique is essentially the technique that Mark was discussing on Monday, except for the fact that I'm only really interested in getting these accurate to within a pixel, right? So if I compute it more accurately than that, it's not going to show up on the picture. So that's essentially just a few orders, a few significant digits. So not anything like 25. So we can actually be much faster in the calculation because we really don't need to be quite as precise in order to locate these well enough to plot them. Yeah, so just to show you another sample, if I move slightly off the symmetric situation, then everything gets kind of messed up. You can see some hint of the previous picture in this picture. The range is more or less the same. I think this goes up to 10,000. And the basic pattern is still there underneath, but the lines are so perturbed and jumbled that they all kind of pile up. Anyway, so that's some picture of the distribution that we're trying to understand. There are many things in these plots that we don't yet know how to describe theoretically. For example, many of the plots show these huge regions off to the left that are resonance-free. And I have no theoretical explanation for why there should be resonance-free regions over on that side of the picture. But I'll discuss conjectures involving this distribution later. I just wanted to show a few preliminary pictures. Let me close this down and go back to my talk. This is going to work. So well, in the first place, it's foolish, I guess, to survey such a big subject, especially while I'm being filmed, because I'm undoubtedly going to leave out people's names that I shouldn't have. And so I just want to apologize in advance if I have not gotten all the names that I should be putting in here. It's not intentional that I've left anything out. It's just it's a big subject with a lot of different results, and it's hard to include the whole picture. I decided to try to sort of organize the survey based on approaches rather than on results, because for each one of those categories I discussed in the first slide, there are sort of many layers of different results that were proved over the years, and it's very difficult to trace the full history. But I just want to give you some idea of all the different kinds of techniques that have been brought to bear on the problem of spectral theory, particularly in the case of infinite volume. So finite volume falls into the purview of traditional Selberg theory of automorphic forms. So in some sense, there's a much longer history and much greater literature in the finite volume case. And so I just want to emphasize that I'm not trying to summarize the finite volume case in this list. I'm just trying to indicate some of the developments that have affected the infinite volume situation. And so one way to approach this problem is through just sort of traditional spectral theory and scattering theory. I think in the hyperbolic context, that idea was introduced by Fadeev. I mean, traditionally, scattering theory applies to potential and obstacle scattering in Rn. So physicists typically have done scattering theory for a long time, but most of it is scattering theory for Schrödinger operators or for obstacles in Rn. And so interpreting scattering theory in a geometric setting, particularly this hyperbolic setting, I think was in the 60s, Fadeev was the first to suggest that. And then various other people worked on this problem from the viewpoint of traditional scattering theory, and particularly the basic spectrum, essential spectrum and discrete spectrum that I discussed a few slides ago. It was worked out just from the traditional viewpoint, where you study the scattering matrix in terms of the limiting absorption principle, and you can sort of approach it in terms of techniques that work for Schrödinger operators and prove many of the basic spectral results that way. Of course, you can approach it from the point of view of Selberg theory, thinking of this as a theory of automorphic forms and harmonic analysis and representation theory. So Patterson was, I believe, the first one to sort of write down the zeta function in the case of a manifold that was infinite area, surface that was infinite area. That's not part of the traditional Selberg theory. Selberg theory, of course, generally is focused on arithmetic cases, which generally are finite volume, unless you take some subgroups, as Frédéric did in his talk on Monday. So in that context, you can develop a theory of the zeta function, and the main focus is on the Eisenstein series, and you interpret the scattering matrix as sort of an interpolator between Eisenstein series. And there's various results that were obtained from that viewpoint. And then there's also a sort of dynamical way to look at this whole thing in terms of transfer operators, relation between dynamics and the limit set. This was a program instituted by Patterson in this particular context. Of course, the dynamics go way back before this, but for this particular setting, to sort of interpret the problem dynamically, essentially Patterson's first paper on this subject introduced the idea that you could relate the limit set to the first eigenvalue of the Laplacian, for example. So this theory again applies just to hyperbolic quotients, and it gives you some picture of what the first resonance is in terms of the dimensional limit set. I'll say more about that in just a second. It gives you an interpretation of the zeta function in terms of the Ruel zeta function, and so it allows you to sort of connect the dynamics of the classical geodesic flow to the spectral theory of the Laplacian. In particular, certain results are obtained this way, results on the spectral gap and the fractal resonance bounds, which I'll discuss in more detail in just a second, are obtained by sort of this consideration of the dynamical, of the transfer operators. You can also approach the whole problem from the point of view of microlocal analysis. So this was I think the first microlocal interpretation of this in this setting was the Matteo-Melrose paper that's been mentioned earlier. That generalizes, all the previous results are restricted to hyperbolic quotients, and this suddenly generalizes to metrics that are only asymptotically hyperbolic. The definition of asymptotically hyperbolic has already been given several times, so I guess I won't repeat that. And this is an approach that sort of first reveals the structure of the resolvent. So previous approaches, you can sort of describe the scattering matrix, but this is the first time that you really sort of understand the structure of the Schwartz kernel of the resolvent from this viewpoint. So it gives you a proof of analytic continuation, but it also gives you sort of structural results about the kernels of the operators. And until relatively recently, that was essentially the main thing that we got out of the microlocal approach was sort of structural information about the nature of the operators. We really couldn't get estimates, growth estimates or high-frequency estimates from the Matteo-Melrose construction because of the iterative construction of the boundary made that very difficult. And so that changed relatively recently with the work of Andras that's been part of the estimates that he needed for the work on black holes that was discussed yesterday. Involved needing to prove high-energy estimates of the resolvent for asymptotically hyperbolic manifolds. And so he developed a sort of new approach to the analytic continuation that would allow you to do that. Sort of typical fashion for Andras, he sort of looked at the problem and thought, well, the proper way the proper setting for this problem is the following, and then it was all easy based on that. And so that has led to other applications on both spectral gap and fractal resonance bounds in the work of Dachev and Dyatlov that were not possible from the microlocal viewpoint before Andras's new approach. So I'll mention some of those actual results later on. And finally, there's a school where sort of introduced by Guillaume and Zworsky of studying the zeta function in terms of regularized traces, or studying the spectral theory in terms of regularized traces, sort of doing the same kind of trace formula you would do for a compact manifold, except the operators you're considering are not trace class. So there's quite an innovation there to figure out how to define a trace in the situation where the operators you're interested in are not trace class. You still want to have a trace formula that gives you some of the same information it does in the compact setting. So this has been exploited in various ways, for example, in terms of resonance counting and asymptotics. This is essentially for certain asymptotics, this is the only way we know how to do it. Ultimately, writing down these regularized traces allows us to compute asymptotics in terms of special functions, and for certain asymptotics, that's the only way we know how to get them. So I'll discuss some of those results later on in the context of surfaces, but I just want to kind of outline all these different approaches. The classification is not completely disjoint. There's a lot of overlap between the different approaches. But one of the nice things about this subject is the way that all these different viewpoints can kind of mesh together and help you understand the picture of the spectral theory. All right, so I'm going to focus attention on hyperbolic surfaces mainly for the rest of the talk, just to avoid having to describe results in all different layers of generality, but I'll try to indicate some of the generalizations as we go. So one of the first theorems about the spectrum of the Laplacian in this context is Patterson's work in 1976, where he identifies the first resonance, or the first pole of first zero of the zeta function, if you like to view it that way, with the limit set of a group. So this is in the case of an exact hyperbolic quotient. You can think of the group as acting by isometries, Mobius transformations of the Poincare disk. And so here's just a picture of a simple group. This is actually the picture of a manifold that would correspond to a quotient like this. And you'd pick any point you like, for example, the origin, and look at its orbit under the action of this discrete group. And it accumulates on the boundary of the Poincare disk. And that is the limit set, you can sort of squint and see kind of the limit set as the dark, cloudy parts at the edge of the circle. It's a set of accumulation points of that orbit. It doesn't depend on which point you take for the orbit. And it's a Cantor-like set, and this is the Hausdorff dimension that will show up everywhere as a sort of fundamental quantity for these hyperbolic quotients. So by first pole, I mean that, let me start drawing a picture here. So that basically the first piece of spectral information that we get from this result is that this value of delta is the location of the first resonance, meaning that there are no other resonances to the right, and there are no other resonances on the same line as delta. If delta appears over here, then it's an eigenvalue. And if it appears over here, then it's just a resonance and not an eigenvalue. So this is 1 and this is 1/2 in this case. So in particular, you only get discrete eigenvalues if delta is bigger than 1/2. And so in that situation, the first one would occur here. There's a beautiful recent result of Ballmann, Matthiessen, and Mondal from just last year, which actually tells you how many eigenvalues you could possibly get. So the number of the discrete eigenvalues all appear in this region here. So this is S in the interval 1/2 to 1 corresponds to the eigenvalue in 0 to 1/4. And the limit on the number of eigenvalues is at most minus the Euler characteristic. So in this case, the Euler characteristic is -1. So there's at most. So if there is one eigenvalue there, then that's the only one. If delta is on this side, then there's only that one eigenvalue. All right. So then, of course, we have these. After we have figured out analytic continuation of the resolvent, we have poles of the resolvent appearing over here. And so some of the earliest work on figuring out how many poles there are is a bound by Guillaume and Zworsky that tells us an upper bound, which is not a fairly something that's been established in various other contexts at this point, but also a lower bound, which is quite remarkable and relatively rare. This is the first time you had a lower bound on the resonance count in a sort of non-trivial case, the dimension higher than 1. So it tells you that you can draw the circle wherever you like, but it makes sense to center it here at 1/2. And so if you draw a big circle like this, then the number of resonances is comparable to the radius of the circle to the squared. So, of course, the area of the circle is comparable to t squared also. So roughly what that's telling you is that you expect sort of uniform constant density in this region. Sorry, let me say that differently. If these were distributed uniformly, you expect the density to be constant. There's no reason that you expected the distribution to be uniform, but it's just to sort of give you a picture of how many resonances there ought to be in a circle like that. So that's been generalized in various settings, higher dimensions, and also to manifolds that are hyperbolic near infinity. And most recently, Colan and I were able to generalize this to a case, at least the upper bound, to a case with non-maximal rank cusps in higher dimensions, which was quite involved, but it's basically, in some sense, a very similar argument to the original Guillaume-Zworsky approach, just rather complicated in the case of these cusps. And then also a lower bound of the same type has been generalized to higher dimensions in the hyperbolic case by Peter, and then in a paper of mine in the case of a surface that's manifold that's hyperbolic near infinity. All right, so another thing I wanted to mention at this point is just that you can get, in the case of surfaces, a sharp constant for this bound. for the upper bound. So this expression that appears on the right, this integrated form of the counting function, is the expression that you see when you try to count zeros of an entire function using Jensen's formula in complex analysis. So it's essentially a Jensen's formula argument that gives you this, estimate of the integral. And it's really a special function estimate that allows you to pull out this constant. And this is sharp in the sense that, well, sorry, let me explain what k is just in this simple picture here. K is the core of the manifold. So K, for any of these manifolds, I can sort of, the funnels will be bounded by closed geodesics. And so I can identify a sort of convex core of the manifold by just taking the manifold with boundary that, where I lop off all the funnels. If the manifold happens to have cusps, then I just leave the cusps. That's still part of the convex core. So I end up, once I lop off the funnels, I end up with a finite volume manifold, which in some sense, its volume is the regularized volume of the original surface. And so the upper bound that appears over here, this is just the Weyl constant, right? If you had a compact manifold, that would just be the Weyl law that told you that constant. And then there's a contribution from the lengths of the funnels that you've lopped off from the LJ, or these lengths of the pieces that I've left out. So that constant is sharp. We don't have a Weyl law for the resonance, but if we did, that would need to be the constant that occurs in the Weyl law. Okay, so on to the sort of more recent work on sort of location of the resonances. First thing I want to consider is the spectral gap. So this has already been discussed in various talks this week, but let me just remind you of some of the details. So if delta is bigger than a half, as it is in this picture here, then the fact that the spectrum over on this side is discrete tells me that there's always a gap between delta and the next resonance, right? There can be no other resonances above or below if I'm on this side of the critical line. So there must be a gap there. And it turns out that there's also a gap on the other side. This was a groundbreaking theorem that Frédéric proved in 2005, that even if delta is less than a half, there is a resonance-free region to the right of delta. So let me just try to draw the picture here. So if I have the critical line over there, and delta is right here, as it is in all of the plots that I'll be showing you, then there's some epsilon width such that there's no other resonance to the right of that line. Okay, so some of the other things that we've figured out recently, work of, so that original proof is based on the dynamical, the sort of transfer operator viewpoint. And then using the trace formula, Jacobson and No in 2012 proved sort of bound on the other side that Frédéric mentioned in his talk on Monday, that if you go from delta over 2, so right there, if you go to the right of that by delta squared plus some small amount, so some line right here, which is, this is delta minus epsilon, and this is delta over 2 minus delta squared plus epsilon, then to the right of that line, we know there are infinitely many resonances. So in particular, there are infinitely many in between here. We know, of course, that from the lower bound of Guillaume and Zworsky, we know there are infinitely many if we draw a disk like that. But this tells us that infinitely many of those lie in a strip. And finally, a very recent result, this is still just a preprint by Bourgain and Dyatlov, tells us again in the convex, in the exact quotient case, convex co-compact group, so meaning the manifold has no cusps. Then it's sort of the complementary situation to Frédéric's result. So if delta is less than a half, then the result of 2005 tells us there's a gap. And what this recent result of Bourgain and Dyatlov tells us is is that if we have delta over here bigger than a half, then there's still a gap on this side of the critical line. So there's still, this is 1/2, this is 1/2 minus epsilon. And it tells us that there can only be finitely many resonances to the right of that line. So in other words, the resonances cannot accumulate on the critical line, which is a very interesting result from the point of view of physics, because the resonances, as they get close to the critical line, the distance to the critical line is really the decay constant for the resonance. So the resonances that are close are sharp or metastable, if you like. And so this is putting a limit on how sharp the resonances can be. So this tells us something about the distribution of the gap, that we know that there are a certain number of resonances in a strip, but also we have some limit on the right side of that strip, that there's only going to be finitely many beyond a certain point. There's some conjectures that go quite a bit beyond this that tell us that there are, for example, the conjecture made in that paper that, for which I just quoted the result, says that the essential spectral gap is delta over 2. So what that means is that we expect that the dividing point between, basically expect these lines to come together. We know that there are finitely many resonances to the right of this and infinitely many to the right of this. And the conjecture is that those lines can be pulled together to delta over 2, so that if you have, let's draw another picture here, so that if I draw, here's delta, and this is delta over 2, that there are only going to be finitely many resonances to the right of delta over 2 plus epsilon. And if I go to delta over 2 minus epsilon, they're going to be infinitely many. So in some sense, that means the resonances are somehow going to be concentrating near that line delta over 2. So there's a theorem in the finite volume case of Selberg. So in the finite volume case, delta is equal to 1. There's a theorem of Selberg that says the resonances accumulate on the line 1/2. So this is consistent with Selberg's result in the finite area situation. And there are various sort of heuristic arguments why we might expect this to be true. And I'll show you some numerical evidence of it in just a second. Let me just mention that this result that I described of Bourgain and Dyatlov was, has led to a conjecture that Maciek made this is in a survey paper that came out just last year, that whenever you have an asymptotically hyperbolic manifold with compact hyperbolic trap set, then there should be an essential spectral gap that is between the critical line, this is basically this picture here, between the critical line and the first resonance, there should be a gap in the case when the trap set is hyperbolic. So the theorem of Dyatlov and Bourgain includes, applies in other, I guess it's not, I guess it's probably Dyatlov and Joule, the other case where you get a spectral gap in a situation with a hyperbolic trap set. So if I would highly recommend Maciek's survey article that he posted just back in the fall, I guess, if you're interested in kind of finding out some of the background on these conjectures that I'm going to describe. So when I first started doing numerical calculations, one of the goals was to try to find some evidence for this conjecture, the one at the top there, Jacobson and No. And at first, the calculations were so limited that it was rather difficult. But I think as we get more and as we get better at doing these calculations, the evidence gets stronger and stronger. Let me just show you a case. So this is the designation X669 means that it's a surface like this, and the lengths are 6, 6, and 9. So this is, maybe I should just label this one. This is a case of X, L1, L2, and L3, just to have a way to distinguish these things. We can only really do the calculations effectively when the Euler characteristic is -1. So we have this setting, and we have a torus with a single funnel, and those are the only cases that we can really do very, very well. So I have calculated the resonances for this plot. I've basically gone from delta to 0, and I've divided this up into 5 bins. And then I have calculated the resonances at intervals of 100. So I'm essentially calculating the resonances in each bin using just the argument principle, just sort of integrating, figuring out the change in argument of the zeta function around the edge of the bin tells you how many resonances there are inside. And so if I calculate the, if I plot the count for the resonances that are in the furthest bin, like in the furthest row, so that is this one over here, this is, according to the conjecture, this bin is meant to empty out as you go. And so you can see that indeed, at first there are a number of resonances in that bin. I don't know if you can see the number, but the count goes up to maybe 15 at the maximum. And so at the start, you see some sign of resonances in that bin, but there are vast regions where there are none. So according to the conjecture, eventually this picture just goes completely flat. And when we first started to do these calculations, we were in this region, and we didn't see any evidence at all. But now that we can go further, we do see sort of vast regions where there are no resonances, which agrees with the conjecture. Just to show you what, to compare that, let me show you the comparison between the counts in the first 3 bins. So now I'm going to plot the counts of resonances in this line, and then the middle bin, which includes delta over 2. So the blue is the middle column. And so you can see there are hundreds and hundreds of resonances in that column in each bin. And then the next line over is this fourth column, and much reduced and seems to be approximately flat. There's no sign of growth in that bin, or at least very little. And then the count that I showed you in the picture up above is vanishingly small. It's a little hint of green down at the bottom, but it's essentially 0 from this plot. And just to show you another view of the same picture, I can do a sort of contour picture. Let's see if this shows up. Yeah, so here's a sort of contour plot of the density of resonances where delta is over here, delta over 2 is in the middle, and this is 0 on this side. And this is going from 0 up to imaginary part equals 100,000 at the top. And the color essentially gives you the density of resonances. You can see that these parts are very dark. The conjecture is that eventually they go black. And we can see that already this 5th column looks completely black. And the resonances do seem to be piling up. The other part of the conjecture is that there should be infinitely many in the center if we keep going. And they do seem to be piling up in the center. One of the features that we don't have any conjecture or understanding of at this point is that the distribution seems to fall off on this side of delta over 2 as well. So if you look on this side, you see some black regions, and you see generally a much lower density on this side of delta over 2. Not quite as dramatic as there, but I'll speak of this more later on. There's a conjecture that most of the resonance should actually lie in the middle of this line, and we do see some numerical evidence for that. Let me just show you another case of the same thing. Just, there's only so far you can get with these numerical calculations, but they do start to give you some idea of the whether or not we can detect these phenomena occurring. So here's just another of a similar plot. This is 889 in this case. And just whenever you plot this, you see more or less the same pattern of resonances piling up in the middle column, essentially vanishing from the columns close to the critical line, but also a much lower density to the left. So I will discuss that in detail. In case you're wondering what the counts are, I can actually add up the number of resonances in each bin. So this is just the total for going up to, in this case, I think it's up to imaginary part equals 600,000. You can see in the middle, I've got almost 1.5 million resonances in the center column. So getting close to infinity, I would say. And then in the next column over, relatively small amount. And in the column near the critical line, in this case, I can't even pull it up. I think it's about 8,000. Yeah, there it is. So, the number of resonances over here next to the critical line, vastly smaller than what we get at delta over 2. So, all very good support for this conjecture at this point. Much better than we could show even just a couple of years ago. All right, so back to the talk. All right, so that's the spectral gap conjecture. It's a sort of picture that's emerging of where the resonances ought to be located that we have some at least corroborating evidence for. Another big topic recently has been the existence of fractal upper bounds on the resonance set. So for this discussion, make sure I'm not going to run out of time here. Let's see. I will move over here. So for this discussion, I'm going to consider a local counting function. So what we're going to do is choose some value sigma. So delta is here. All of the resonances are essentially are to the left of delta. And we're going to count the number of resonances that are to the right of sigma at some height. So we pick some height t. The width of this box is more or less arbitrary, but it's we're basically interested in how many resonances are in a box like that asymptotically as t gets very large. And there's a conjecture that says that the count of resonances in some vertical strip parallel to the critical line should be given by a power law, and the exponent should actually be given by the dimension of the trap set. In the case of a hyperbolic quotient, this basically says that if I integrate this local counting function going up in the vertical direction, the dimension of the trap set in this particular setting is related to the dimension of the limit set. It's 2 plus 2 delta, so half that is 1 plus delta. And so the integration of this local counting function as you go up is expected to have this behavior, according to this conjecture, which is motivated by work in the early 90s of Sjöstrand that suggests that such a power law ought to hold. And at least on the upper bound side, the result is proven in a paper, in this context, in a paper by Guillaume, Lin, and Zworsky in 2006. They proved not just the upper bound on the integrated counting function, but on the local counting function, that it behaves as a power law with order t to the delta as the bound. And if you integrate that, of course, you get t to the delta plus 1 for the conjecture. So that tells you that the upper bound agrees with the conjectured upper bound. That result has been, well, the original result applies in higher dimensions as well, for Schottky groups at least. And then that's actually been generalized in relatively recent work of Dachev and Dyatlov. This is some of the payoff from Andras's big innovation in the meromorphic continuation argument, is that you're able to prove things like this fractal upper bound in the case of asymptotically hyperbolic manifolds. Okay, so recent work on this by No and then a sort of improvement of the same result by Dyatlov, just I think not published yet, but just came out a year or two ago. gives you indication, again, of this same kind of phenomenon we're discussing with the spectral gap of the fall off in the distribution as you go to the, towards the critical line. So what this says is that the upper bound, if you go to the right of delta over 2, it says that the exponent of the power law decreases down to 0 as you get towards delta. So basically let me just see if I can graph this over here, that if we're looking at the exponent in the upper bound, the Guillaume-Lewin-Zworsky result tells you that the upper bound of the exponent is delta, and this more recent work tells you that after you hit delta over 2, that exponent goes down to 0, starting from delta over 2, give or take an epsilon in the error term. And so as part of this work of Semyon, Tobias and I helped out with an appendix where we tried to check numerically if this is, the estimate is relatively sharp. And so we have some evidence for this. So let me just try to indicate a little bit what this plot is showing. So in the asterisks, which you can sort of barely see, hopefully, that are down here, we have done a linear fit to the integrated counting function. So we take essentially the counting function integrated up to a point t. We plot that on a log-log plot, do a linear fit, and read off the exponent, and you can see it comes out way, way below what we'd expect from the theorem. And that's essentially because there are large regions that are empty, where there are no resonances. So if you think about it, let me draw a picture of it over here. What we're getting is the theorem describes the maximum value of this local density. So if I look at imaginary part going this way, and I graph the density, then what I see are large regions where I have zeros. So roughly speaking, I see something like that. And so if I just do a linear fit, I'm sort of basically being influenced by all these zeros, and I'm getting a slope that's negative, and that's what's happening with the asterisks. So what we decided to do for this numerical study is to study the convex hull of these peaks, because after all, the theorem is telling you about the maximums. And so if we do a fit to the maximums of these peaks and ignore the zero regions, then those are the circles. And you can see the circles are fairly close to the value predicted in the theorem. And this orientation of this picture, by the way, this essentially along this axis is distance to the critical line. So it's roughly speaking just reversed from what I've drawn there. So we can see, I would say the accuracy is even a bit suspicious when you get over on this side and you see that we get actually very close to the value of delta in our estimates. I'm not sure I believe that that's as reliable as it looks, but it at least is certainly, philosophically in agreement with what the results show. Okay, so I'm going to try to wrap up quickly here. There's one more conjecture that has appeared mainly in the physics literature, mainly in numerics and also in experiments in the physics literature. It's kind of a heuristic that comes from quantum mechanics. So this has already been brought up in previous talks, that the associated to these resonances are resonance states, and you can assign a decay rate, which is essentially distance to the critical line. The frequency is the imaginary, in this picture, the frequency is the imaginary part, and the distance to the critical line is the decay rate. And that's the quantum mechanical decay rate of a state. On the other hand, you can measure a classical escape rate by looking at the sort of neighborhood of the trap set and studying geodesics that are near the trap set and looking at how quickly they diverge out of the neighborhood of the trap set. There's an exponent associated to that divergence, which in a paper of 2005, Friedrich computed in terms of the, again, in terms of the dimensional limit set. So the classical escape rate is 1 minus delta. And then in quantum mechanics, you know that the density of a state is given by the square of the wave function so we'd expect, semi-classically, that the resonance states should somehow have a decay rate that piles up at a decay rate that's half of the classical rate because of this square in the density. So if you put those together, that this value should equal half of that value, that tells you that the resonances should, again, the same conjecture we've been looking at before, that gives you another way to understand why you think the resonances should accumulate on this line in the center. So, and indeed, so what we see in these pictures is essentially what they see in physics experiments, say for n-disk scattering systems, for example. When they plot resonances, they see a peak at the location equal to half of the classical escape rate, which in this picture is delta over 2. So that's another reason that we might expect that the resonances are piled up in this center channel and actually falling off in density as we go to the left of it. All right, so I'm almost done. I mean, you should take these numerics with a grain of salt. They're meant to just kind of be amusing illustration and motivation. Of course, you can never actually demonstrate anything asymptotically with a finite calculation, but we can at least see that we see some strong evidence that the things that we believe to be true are actually going to happen. I just want to finish with one last picture of resonances. Let me shut this off. I think the most intriguing picture of the resonance plot that I've been able to generate is this one, which is the plot for a torus. This is what you get when you, I hope this is visible enough. There's sort of fine lines here that are weaving back and forth in this pattern. It's really quite pretty if you can see it. If I increase the density, they get a little bit closer together. Let me see if I can sharpen it up just slightly. Yeah, too much. All right, I'll give up with that. That's just slightly darker. Anyway, so this is this pattern of resonances for a torus with a single funnel. So there's a funnel attached on this end, and in this case, these are parameterized by lengths over here. There's 2 lengths. And then there's the angle between these 2 geodesics is also one of the parameters. Let me just denote it here by theta. So I can parameterize this by that set of numbers. And this is the case that I plot here, where I take the lengths to be equal and the angle to be a right angle. So this is actually y66 pi over 2. As you can see, it was labeled at the top there. And so I've been trying to figure out why this pattern is so nice, because it doesn't show up in any other case that we've been able to plot. It doesn't look at all like the other pictures. And so in trying to figure out what's going on, when you look at the sort of Schottky representation of the group in this case, you see that it has the symmetry of a square. There. So if I represent this as a Schottky group, the generators map circles to circles. And in particular, for the torus, the generators have to cross. So one of the generators will map circle number 1 to circle number 3, and another will map circle number 2 to circle number 4. And of course, you have their inverses as well. And if you have this setup where the 2 lengths are equal and the angle is pi over 2, then you get reflection lines, as I've indicated in red. You get a set of 8 reflection lines four reflection lines that essentially give you the symmetry of a square. So there's another way you can get the symmetry of a square, which is by pairing up the circles differently. So you take the same Schottky picture, but you pair disk number 1 with number 2, and disk number 3 with disk number 4. And so if they don't cross, if the generators don't cross, then I get a pair of pants. And so if you work it out, if the pair of pants has the same symmetry of a square, then that corresponds to the case where one of the lengths is twice the other two. So the two of the lengths are equal, and the third one is double. That's the same symmetry pattern. And so just out of curiosity, I plotted that. And remarkably, it ends up looking the same. So there's another mystery that I don't have a great explanation for. So one of these pictures was this topology, and the other picture is this topology. And all that seems to matter is the symmetry of the fundamental domain. The topology does not actually seem to affect the dramatic structure of the picture. So somehow this beautiful pattern is associated to this symmetry of a square. And it would, I don't know if it's mathematically all that interesting, but it just aesthetically, it would be nice to understand why, why it generates this particular pattern, even in a different topology. All right, so I will stop at that point. I think I'm right at the ending point.
So thank you. I asked the questions we asked in the microphone here, so if anybody has a question.
Can you just say what are the parameters for this picture?
This is actually 6612.
6612. What is?
Yeah, sorry.
Yes, what is 12?
6, 6, and 12 are the three lengths.
Oh, right. Okay. And in the corresponding picture for the tori?
Is the 6 pi over 2.
Oh, 6 pi over 2.
Right. So in the torus picture, the two lengths are these two.
Right. And what is the imaginary part of this picture? What's the largest imaginary?
I believe
I
it's
just
easier to
can't
see.
see it.
4,000.
Oh, right. Okay. Thank you.
Hello. Just out of curiosity, when you said the pictures are the same, they're really the same, or just by your?
No, just the same structure.
Same structure,
so
right?
Not
because
literally
was,
the same.
Yeah. Okay. No, because I okay. Yeah, okay. I see. Just by phenomenological. Okay.
But I mean, it is interesting. There's a theorem that the set of resonances determine the Euler characteristic. Mm-hmm. But not the topology. So you can basically prove that theorem by studying the zeta function and their topological zeros of the zeta function, as we saw in previous talks. And so if you read off the order of a topological zero, you determine the Euler characteristic. Mm-hmm. So we can figure out the Euler characteristic based on the resonances.
Okay.
But there's no theorem that says that it couldn't be exactly the same. So if it's got the same Euler characteristic, then in principle, there's nothing that we know that says that you couldn't have exactly the same pattern. I don't think we believe that that's possible, but it's especially at this low genus, we wouldn't expect that to be possible. But in this case, they're not literally the same. Okay. They just look quite similar. So this pattern goes up to 4,000, and if you plot the previous, sorry, let's see, where's the other pattern? No, I take it back. They both go up to 4,000. So if you superimpose them, they look almost identical, but they're not exactly lined up.
Mm-hmm.
What is the characteristic? What is the imaginary part of the characteristic?
Wait, say that again?
What is the imaginary part of the characteristic of the first intersection?
So right there, that's up at about 800, where that first occurs. Oh, and incidentally, all these points where the sort of nexus where all these lines come together, as you can see, happens regularly. That's always delta over 2, as the conjecture says it should be. In fact, another way you can see the The conjecture is just to plot a histogram of the real parts of the resonances. And you can see very sharp peak, again, exactly at delta over 2. So.
Okay. More questions? Okay, so let's thank the speaker again.